Hi everybody. Let's get back to our data systems again. This one I'm going to talk about multiplexer with show you how to use the multiplexer, and also we will go to PSPICE using the multiplexer 74151. Actually we have this the multiplexer in the library of the PSPICE. Okay, let's see. This is one of assignment that I got when I studied master degree in microelectronic manufacturing at Rochester Institute of Technology, as I mentioned earlier. This is the reference textbook again. Data System by Professor Perman, who is the editor of the book. So for this series, I will take you through the multiplexer for the actual work that you actually can do, the real hardware, when you get the multiplexer for 74151A, and you can assign your output as the desired. Let's start with the assignment here. The objective to become familiar with the design procedures involved in the use of multiplexer as logic elements. So by using the multiplexer 74151, realize the following logic. So this is your output function that depends on the input A, B, C, D, and what we're looking for is the A complement, or with B, C, D complement, or with B complement C, D, and use the control variables A, B, and C. Notice that there is an input label, output enable, or OE. This input is low true unless the output are enable. So when you have an input or E be low true, it will never change the state, I mean the output. And F, that means you will get your output to be low or zero at for any combination of inputs. And also assign A as the LSB input, or the least significant bit. Okay, so that's an agreement for the assignment number 4. Now let's start with multiplexer 74151. That's the 8 input multiplexer, and realize the following logic. That's what we're looking for the function. So let's go through the truth table. Let's write down all 4 inputs. So you have the total of 2 to the power of 4th ray combinations. So you have 16. So you can write A input B, C, and D. By following the function, this is what you're looking for. A prime, B, C, D, complement, B, complement, C, D. And then this is your function, okay, or your output. Now from the truth table, you can write a complete kernel map from the truth table. So basically you just write down the input A, B, and C, D. So this is your A, 0011, B, 0110, and C, 0011, D, 0110. and you can put ones in color map. As you can see here, this one for your output. When you have the combination of A, B, C, D, that's 0, 0, 0. That's give you output 1. Okay, just refresh about how to create a color map. So this is your AB 0, 0, and then our CD 0, 0. So you put 1 here, and let's see another example here. You have our ABCD 0, 1, 1, 1. Let's give output to be 1. So 0, 1, and then 1, 1. That's also give you 1. Okay, you can work out for the rest. So you can fill up your color map. So now the third step, you are going to create the truth table. So we can draw, like do the connection of your circuit for the multiplexer. The truth table control variables is only A, B, C. When A is the LSB, or least significant bit. So you start with C, you have for low and for high, and B you have too low, too high, too low, too high, alternately. And what about this one? This one has this is the enable pin or selected. So when it's go high, you are set your output. This is your output is Y to be low. So CBA in the state don't care. And this is Y complement. It's going to be your inverse of your Y. So low become H, H become low. Okay. So L here actually represents the logic 0, and H represents the logic 1, right? You know that. Now when you're enabled, become low or logic 0, you will have also the selected input that's assigned to be D0, D1, D2, D3 to D7, okay, according to your input CBA. And if you take a look at the multiplexer, okay, let me go to just to point it out. This is your multiplexer layout. Let me blow this up a little bit. That's the 74151. As you can see that you have a selected input S0, S1, S2 according to the pins number 11, 10, 9, and this is your enable pin, and this is your I0, I1 to I4, which is the equivalent to our D0 to D7, and this is the logic diagram. Okay, so you have 8 AND gate, and they all go to 8 input NOT gate. That's how you do the multiplexer. Sorry, and this is your selected input. This is your enable pin, and this one simply become S2 complement. So go for input. So or S2 prime, and this one back to S2 because the invert and invert skip your normal S2. So you also go to the AND gate. Okay, just wanted to point this out for you. So you have for you know the truth table for your corresponding input CBA and also your output. Okay, but first of all, you're probably wondering how I get this the D prime. Okay, so let's take a look from the kernel map to create your truth table. You check this one out. So A is the least significant bit. So we're going to start from 0, 0, 0. Okay, if you take a look at this one, 0, 0, and C actually 0 right here. So this is your output Y. So it's become 1, 1. So you put here 1. Okay, and then the second one, 1, 0, 0, 0. Okay, 1, 0, and C is simply 0, so you get this one, the output. So become you put 0 right here. Now, why do I have for the complement here? You take a look at the input. That's 1, 0, 1. 1, 0, and this is C is 1, so you have this one. It's not neither 1 or 0, but you have to take a look at another input D. As you can see, this corresponds to this is supposed to be just D, right? Not D prime. Sorry, my mistake. Okay, you can correct this by yourself. Okay, let's check this again. A is there. This one is 1, 0, 1. 1, 0, 1. Okay, so that's give you the output to be 1 and 0. That corresponds to the input. So this is supposed to be D. All right. That's how you get a truth table from the kernel map. Now let's go to your PSPICE multiplexer. This one actually, as I mentioned earlier, that already in the PSPICE library. You can check Control G, and that's what 74151 here. This is your multiplexer. So it's labeled the same as in the data sheet. Okay, so it's the same. For Y, that's a pin number 5, equivalent to Z. And for enable pin, that's the 7, right? And selected their input, that's their A0, S1, S2, that's 11, 10, and 9. That's their 11, 10, and 9, okay? Now let's work out on PSPICE. Just to, I actually redraw this for you. So basically, since the A is the least significant input, so A go to A0, okay, and C the most significant bit. Let's go to S2. By doing this, you have to wire to your I0 to I7. That's how you work this out, according to your truth table that you had, that we create. Okay, that's going to get smaller here. So what I used, let's go back to the truth table here. All right, so by starting from low, 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 you have your output to be 1, just reminded you that how we get this one is we need to set up the function that we are looking for first, and then you work through all 3 steps. So for low, that corresponds to the 0, and you need to connect to the logic 1 or 5-volt high voltage, right? So that's why for the 0, where's my D0? That's the correspond to I0 here. I connected with the clock. Actually, my digital clock, I put attribute as the on time to be 10 seconds. Okay, because you have only 8 combinations, 2 to the power of third, because you have 3 inputs right here, right? You don't need to care about the enable pin. So I simply put this one for 10 seconds. Even we need only 8 seconds for one period of the C input. Okay, so they all go to stay at logic 1 all the time. What about I1? Take a look at this one. That corresponds to the 1. That's the what? From D1, that corresponds to 0, right? So this is supposed to be 0. What I did is I just put this one as the no on time, but I put this one as off time, all the time. So I put that 10 seconds. Now, what about D5? This one is simply actually supposed to be D, right? But okay, we just go ahead and do the correction later on. Suppose this one to be D. Okay. So let's look at D5 or I5 here. So you connect it to the D input, and that's supposed to be what? Actually, this one, it doesn't matter because you can change around, but just keep it as the complement. Okay, so I have D input and I put the inverter voltage inverter to do the inversion. So I have this one as the D prime, go to I5 or D5. Okay, so you can do the rest. And also what I did, I shake it back. What about the setup before you do the simulation? You go to setup, and I want to see my digital clock. So I set up the final time to be 10 seconds, right? Because there you have the 8 combinations. Each of them take 1 second. So I have 10 seconds. That's enough. And then you go to simulate. All right. So what we're looking for is what? What we're looking for is that you need to check back with your truth table that you create from Economap. So keep in mind your output is Z at pin number 5, and you also have the input that you're looking for, right? Because you are from your truth table here. You have D prime, you have D, you have the rest going to be 1 and 0. So if you want to do the plot, let's minimize. Okay, that's better. And minimize this one so you can see your along with your plot. Okay, let's go to 10 seconds. That's good enough. So let's, all right, hold on a second. Sorry, got like coming in. If the making sound, I'm sorry, apologize. Okay, let's go on. So what you're looking for is your output Y rate, and you're also looking for your plot, your digital clock need to correspond to whatever you design. So like 10101 D prime 1 D, or the complement. Let's go to Y first, and that is come from U of Z, right? This is your output. Here, what I have. Now you want to check if it corresponds to this or not. I mean, in the term of you put D in the plot. So I add input D. Okay. So let's check carefully. What do we have here? From a digital clock, right? You have A, B, C, D as the input. Need to go back to page number 11. Oops, sorry, I think I missed. Oh, okay, sorry, it's just right here. So that's ABCD is running, like this for your input. So you check with the table from Economap. At 1 second, right? Because this start from so 0. This is for the first one. This is 1 second. You can see that this corresponds to 1, and the second one 0. Sorry, and turn out to be 1, and then 0. But for this timing here, you see that sorry, this still become 1. Sorry, my mistake. Okay, but for this period of time, it seems that need to correspond to the complement. So this is your D, right? Actually, just right here. That's supposed to be your corresponds to your D input. So this has become D. You can see that. Okay, this is your output. And then back to 1. So it doesn't care 1. And then back to what? D. Again. Actually, I had that before. So probably have something wrong with my truth table here. And let's check it out. So that's we go to what, 8, right? 8 seconds. That's 1 period. This is my 8 second. And then back you're supposed to have D for output. So this is the correspond to your D output, right? The input, sorry, that's your output. It's become D. And before that, it stay at 1. And what about here? That also become the param as we assign. Okay, so that's how it works. In the real circuit, you just simply do the connection like this, and you will get your multiplexer work. So basically, for multiplexer, you require selected input. In this case, is A, B, C, but actually it's the S0 to S2, and then also you assign your input for I0 to I7, and then you will obtain or achieve your output. Okay, so that's all about the basic multiplexer tutorials. Okay, I'll see you in the next YouTube. Bye.